Hey everyone, this is Xibei from DoraHacks. Thank you all for joining us today for our Starship Use Cases Hackathon Round 1 demo session featuring Orbital CAN station with Nexus Aurora. We're really happy to have Sam and Camera joining us today. Before we kickstart the session, I'll just give a quick introduction about who we are and what we've been working on to foster space innovation. So DoraHacks is a leading global hackathon organizer and developer incentive platform. We love to support innovation in blockchain, quantum computing, space tech, and other frontier tech fields as well. So we launched the Starship Use Cases Hackathon last October because we believe in the vast potential of space exploration offered by Starship's heavy lift capacity. And our team designed 18 use cases and 2 open challenges for hackers to tackle. We're working on to expand the list at the moment. But yes, through this hackathon, we like to motivate all space enthusiasts with engineering skills and entrepreneurial minds to build their solutions for space. And we just wrapped up round 1 at the end of February, supporting 4 winning projects. And round 2 has been kicked off. The submission portal will be open until the end of July, and with a prize pool of $100,000 US. We are aiming to support more space innovators in round 2 for sure. And furthermore, we have another ongoing long-term space resources and exploration mini grants in place, through which we have so far supported 11 early-stage projects within the space sector. And our support recipients span a quite diverse range, including student initiatives, startups, and open source communities projects as well. So basically, everyone contributing to the space sector is welcome to participate and receive our support. So if you're interested in learning more, feel free to click the links below in the description. There you can find more details about the initiatives. Lastly, for the audience during the demo session, feel free to share any questions you have in the YouTube chat room, and I'll make sure to ask Sam and Cameron your questions at the end of their demo. Now, without further ado, I'm excited to pass the mic to the team. Sam and Cameron, feel free to start. Please feel free to introduce a little bit about yourself and then jump into the demo session.
Thank you so much. Hi everyone, I'm Sam. I'm an engineer at Nexus Aurora.
Hi, and I'm Cameron. I'm also an engineer with Nexus Aurora.
Cool. Thank you guys for joining. Yeah.
Thanks a lot for having us. We're talking about our Orbital CAN station, which is a long-term project we have within Nexus Aurora, looking at the future of space stations enabled by Starship. We applied and were accepted very gratefully to the DoraHacks Starship Use Case Hackathon, looking at doing large-scale orbital science parks using Starship and using Orbital CAN. Which we're going to talk through the engineering behind Orbital CAN, why we built it, why we designed it. We haven't built it yet, unfortunately. If anyone listening has a spare $10 billion, give us a call and we'll put one up in orbit for you. But we'll talk about why we designed Orbital CAN the way we did, the motivations behind it, and how it can be used really effectively to solve the problems facing orbital science. And just briefly introduce ourselves as a group. Cameron.
Yeah, so a bit about us as an organization. Nexus Aurora is a community-based project incubator. Our primary goal is to open source solutions to the complex problems of space settlement, which is why this DoraHacks competition is right up our alley. We're a community-based incubator and developer of different projects, and we accept volunteers from across the entire globe. We are able to provide resources to them and help administer to teams to push forward these open source solutions. And so you can see on the screen a couple of the things we've been working on, particularly this project, OCS, as well as side projects like SAM, which is an open source robotics rover system. And again, our whole goal is to bring people from different fields and open source and access the general public's capabilities to contribute to sustainable permanent space settlement in the future, and bring that from hardware and software design, initial concepts, and then fully flesh those out into prototypes and occasionally the full designs, with the caveat that the OCS needs a little bit more funding than several $1 million to get that into space. But yeah, so that's basically what we do and who we work with, and that's where we are today.
Great. So I'll just sort of wind back a bit in time and talk about what we were trying to do with Orbital Can Station, what the point is as a design project, because it was a long one. It took us about a year to design the whole system, running 2021 through to now, effectively, on and off. So it's a pretty big project, but it has some range of advantages you can get from doing a station design process the way we have. And the first reason is essentially that Starship is a complete step change in capability to orbit, as I'm sure you're all aware. It's radically higher mass, lower cost, higher cadence than anything else. Really isn't Saturn V is the best comparison to it, but much lower cost. So if we have a rocket that big and that capable, we can do something as revolutionary to space stations as Skylab did in the 60s, but at lower cost and at higher cadence and all the other associated things. And the problem with that is it involves going back to the drawing board in many senses and abandoning all the assumptions and the heritage design decisions we have from space stations over the past 30 years of running the ISS. So what we really did for Orbital Can was a complete bottom-up design, going through every system, every subsystem, saying, what can we do to take best advantage of Starship capabilities? Heavy lift, large payload bay, structural bracing all around the sides is an often under-talked about one, regular launch cadence, cheap launch. There's a lot you can do with it. We were asking, what should a space station in 20 years look like? How should it function? Because that's as far away from today as the ISS today is to Mir. It's a real change, and there's a chance to do a real capabilities change there. And we were saying, let's not do an evolutionary process. Let's not build up from like Axiom. Let's do a revolutionary change. Blank slate, go over it. What does that mean in practice? It means going through every subsystem of space station architecture. It's architecture in the engineering sense, the functional diagram of the system, rather than the design of it, like you were saying in building architecture. Going through every system in the architecture, all the way back to requirements and business case level in some cases, asking, why is this here in the first place? And that's things including structure, power and thermal, life support, crew interfaces, payload, data, propulsion, docking, launch systems, how you manufacture the thing. It's really the whole life cycle of the station, every part of it. We evaluated where Starship's abilities what impact the abilities of Starship might have an impact on it. In some cases, that meant building trade studies to redo, sort of go through and analyze whether the current solution is good, whether we want to use a concept that was rejected previously on grounds of cost or mass or something else, or doing some designs completely from scratch, because in many cases, we're working in a field that's never really been touched before by engineering design. We need to go in from scratch. And throughout the whole thing, we were making sure to keep a very wide focus and not just focus on one aspect. It's very easy in space engineering, especially when faced with something as new as Starship, to say, right, we're going to really, really nail cost of manufacture. And we're going to focus on that and ignore everything else. We wanted to look at the design phase, testing, manufacturing, fit out, launch, construction on orbit, operational period, maintenance, deorbiting. The question was, what should this space station in 20 years from now function like, look like, work like? How should it be designed? And that was a year-long process, which was very interesting from my view as a thermal and systems engineer. We had a lot of fun with it. We had a lot of very interesting input from people across the community, talking to experienced industry, to academia, talking to other volunteers like ourselves. And we went through the system level and built up from orbit up to say, what should it look like? And really, it's quite a lot different to how the ISS looks. We can look at the defining characteristics before I get to the fun images. But unlike the ISS, it's very, very modular at very different levels. Lots of part commonality, system commonality, subsystem commonality. This really helps with the design of the system. It means you can have more of a toolbox to play with rather than going from scratch. Helps a lot with maintenance, which is a big problem on the ISS. Modules, both component modules and assemblies within the station and the actual modules it's composed of, more commonly have a single function than on the ISS, where they're very multifunctional. And they're designed to be very cheap to build and quite short-lived. We've got very heavy lift at low cost, so there's no point shifting cost out of launch and putting it back into your systems, making very, very, very over-reliable systems If a part breaks, we can fly a new one. If a module breaks, we can fly a new one. We have Starship now. On top of that, it places crew efficiency as really a key to maximizing usefulness. On the ISS, 1/3 of crew time is spent on maintenance, which is insane. Another pretty big chunk is spent on logistics, just moving stuff around the station. That's kind of absurd if you want to maintain a functional science station that's doing a lot of really high value research. There's a reason ISS crew time costs $10,000, no, $100,000 an hour even. Science in space is valuable. We need to get as much of it as we can, and that means not having extensive maintenance hours, logistics time. It means having the crew be specialized in what they're doing and do it well and effectively. And Starship can enable that in many ways. And finally, there's a great emphasis throughout on easy to design, easy to build, easy to run. Stations in the future should be versatile, they should be expandable. If you want to take the ISS and strap a thruster system to it and take it to the moon, that should be possible. It shouldn't require a complete redesign. It should be something you can do as a reasonable engineering project rather than spending $10 billion having to build a new lunar gateway. The module should be simple to build. They shouldn't require massive amounts of tooling to machine from scratch, enormous machining systems. The maintenance and construction should be streamlined so you can maximize crew uptime, as I said. The system should be interlinked and be able to operate from the ground. We want to treat the space station not like this finely tuned aircraft. It should be like a piece of rugged industrial machinery. And the crew should be like highly trained operators. The key is on uptime, reducing training, ease of use, low cost of operation throughout. Because that's how we get the best value out of it and the most use. So here is an orbital CAN station. It's not necessarily the one, it's our baseline configuration. This was the subject of our paper we presented at the IAC in 2021 even, sorry. And we can start to pull out of it some of the design features that make it so effective in this role. This configuration is a single Starship launch operator, single Starship launch. It goes in a single stretch payload fairing. It's 2/3 the volume of the ISS, about the same power, about the same thermal control, crew of 6 to 10, you reckon, depends exactly on how you fit it out. Split between, let me try and get the laser pointer on, in fact. Split between, can you see that? Yes, we can. Split between a 8-meter diameter module and a 4.2-meter diameter module. This is the same size as the ISS modules. So it's structured in the same way. You have payload racks on all sides of the module and then a corridor down the middle. Great for maximizing the amount of payload in there, but it's kind of a pain to move through. And then the larger module is 8-meter diameters, which is huge, frankly. That's the size of a house. 4 decks tall, split into decks, one of each that keeps work streams separate, prevents usage clashes throughout the whole thing. And this is one of the really key differentiators we have between orbital CAN and the ISS. It's got specialized roles within the system. You're not trying to fit everything into one very compact module. The ISS has this a bit, you have a Columbus lab, and you have some labs and nodes doing different things, but we really went through and said we want to have split space. We want to have habitation and lab and support systems separate. I don't want to be working in a glove box and have a crewman try and get past me lugging a logistics payload out of a Crew Dragon. It should be in a room separate from the corridor. It sounds really stupid, but it's not the case now, and it really should be. It helps with the human factors a lot as well. The design of the actual station it helps with the station module. It helps as well. Both these large and small modules are made of welded sections with stringers rather than machined ISO grids, which is the case currently. And we're switching essentially from old rocket system design like Falcon 9 to Starship, which is welded rather than machined. This makes the design super adaptable. You can just add sections very easily. You can design pre-design this many sections for things like berthing ports, docking ports, which really streamlines the design phase. You'll see some examples later on how that could work. Yes, you can pre-fit in equipment like berthing ports. You can pre-fit in larger things like life support systems. Within each module, again, to help with the design, the vast majority of payload space is in the form of payload racks, which have power and utilities plumbed in advance. So rather than having to reinvent the wheel for thermal management or power conditioning, you have that all on tap for each payload. That makes the design of the payloads and systems inside much easier. Another key function that we're really proud of is the fact it's easy to build and assemble on orbit. We went through and completely redesigned berthing modules and berthing mechanisms because the old ones weren't good enough. The universal berthing mechanism is the next generation way to link these modules together. It functions on orbit, it can function on planetary surfaces. Unlike the current CBM, it's got all the fluid and electrical connections inside the pressure envelope, which doesn't sound like a lot, but that means you can assemble a module and dock two together and link them properly without having to do an EVA, which is expensive and dangerous. It's also got the capacity in terms of electrical and fluid pass-throughs to fit dozens of modules end to end, so you can grow stations in orbit as they go. Again, not easy to build. These radiators and solar panels, which are mounted externally, they're all fitted before launch and deployed from inside. You don't have to have an EVA to go and fit your truss, days or weeks rather than years. And finally, lots of these systems are designed specifically to be very easy to run. Unlike the ISS, unlike Mir, every system that we could fit inside is in the pressure envelope. That includes batteries, reaction wheels, power electronics, commodity tanks, heat exchangers. All of these can be maintained in a short-sleeve environment and replaced without EVA. This is the major thing that they do on EVA and the ISS. If you ever watch a live stream of it, they're going out and replacing failed electronics or failed fluid connectors. We put that inside the station in a safe environment where crew can do it without extensive training on EVA. That's powerful. That helps you run the station. It brings costs down. It brings danger down. And all of this makes the whole thing cheap. It makes it cheap to build, cheap to design, cheap to run, cheap to crew. And that's really the key thing that Orbital Can does as a design. It's using Starship to bring the cost of a space station down in terms of cost per crew hour of useful time on orbit. That's our key metric, down by an order of magnitude, maybe more. Which is really great if you want to build an orbital science park. Cameron.
So now that we've seen the architecture, let's talk a bit about how the station can be used and the potential opportunity that it's going to address. So NASA is currently moving towards the end of the ISS, as we know. They're looking into commercial space station bids and putting millions of dollars into those projects from companies like Blue Origin, Vast, and Voyager. There's China with the new Tiangong station, and then there's additional stations that are being planned. But there is clearly, from this, a demonstrated need to increase our capabilities and the effective time, as that metric is, for being in orbit and to maximize the amount of science yield, science yield we can get there. But there are several inherent problems with existing and planned small stations. As Sam mentioned, a third of the time is spent on maintenance of failing systems, especially as the station gets older. So we want to be able to redesign that and maximize our capabilities as an orbital science park. There are limitations of science, supplies, crew time, and more in existing stations, and design like Starship and OCS is able to inherently address those problems and fix them in order to maximize that science. We do that by leveraging existing planned assets to create low-cost resources and increase accessibility of science in orbit. For example, there were 96 Falcon 9 launches in the last year, and we're about to go into the 4th IFT launch next month. And that is clearly demonstrating that there is already a massive increase in the supply for orbital assets. And so if we have this increase in orbital assets supply, we can now have a massive capability to increase the demand of in-orbit stations and what those stations can do. When you all of a sudden have a much larger space to work with and you have a lot more resupply missions able to go up, and those resupply missions individually also have more space on them, you suddenly get a lot more potential access where you can send more resources, you can send more people can be on the station for longer periods of time and in larger groups, and therefore they can also become specialized and do specialized research on specialized equipment that is sent by companies that develop those parts a lot cheaper, because the access to orbit is cheaper, the time on orbit is cheaper, and the scientific yield is therefore maximized because all of the requirements are lowered. And so as we see, we have an improved supply. So now we can increase demand using the system design of the already designed and already going up Starship and the new OCS design, which we've published from Nexus Aurora. Now that we've talked about that, let's move on to how we remove those barriers to orbital science. So the ISS faces a multitude of challenges that right now, I'm going to use that as an example again, stems from its aging infrastructure and operational limitations. One critical issue is that constrained upmass and downmass capability, as I mentioned. That's exacerbated by dependence on a limited number of supply missions from Earth, resulting in delays and uncertainties in the delivery of essential equipment, consumables, and scientific payloads. We see this all the time. I think recently we had a delay in the most recent crew resupply or crew supply to the ISS, and that happens. So it prevents issues and limits time, increases cost, and has a lot of trickle-down effects. Further, the ISS operates with a generalist crew model, which necessitates extensive ground training for astronauts to perform diverse tasks that includes maintenance all the way up to scientific research. When a small crew has to do all of these tasks, that consumes valuable time and resources, which are limited on the station. Additionally, the confined and more regulated environment of the ISS imposes strict constraints on experimental design and implementation, including limitations on space, power, and resources, also known as SWAP, thereby inhibiting the breadth and depth of scientific exploration and discovery possible on the ISS or similar stations. These challenges underscore the pressing need for innovative solutions and infrastructure upgrades to sustain and advance the capabilities of human spaceflight and research on the ISS and similar space stations. You can clearly see that the existing solution is not as optimized as it could be. And even in the future, where we're putting new funding into new commercial space stations, without addressing these constraints or issues, we're going to run into the same barriers to orbital science, which at the end of the day is one of the core drivers of being in orbit or sustaining a manned presence in orbit. So then compare that to Starship, based on the Orbital Science Station, which benefits from an inherently larger size and standardized infrastructure, which allows larger crews to be stationed and serviced more frequently by additional Starship flights. The benefits free up crew time to perform scientific research in specialized fields and with equipment that's no longer constrained by such limitations on SWAP. Imagine if you are an institution, a company, or even a student that wants to design an experiment for low Earth orbit. You no longer have to compress your design into a 10 by 10 by 10 centimeter cube. You have an oven or a fridge-sized amount of space and mass to work with for a potentially lower cost even. You no longer have to put so much time and effort into just developing the experiment, and you can do more towards the actual collection of data and getting the end result that you're looking for, rather than having to jump through so many hoops, which can be massively expensive in both terms of time and actual cost as well. So these benefits are large standard structure like Starship, which already exists or is already being planned to go into orbit on a regular basis. These bring to crewed habitation of LEO inherently an inherent address of the problems that are currently experienced across all previous and current stations. And Starship is very much a great way to fix those problems because it provides its own massive capability to do resupply and the ability to launch these large modular stations like OCS that can be almost infinitely connected and infinitely supplied. All right, let's move on then and talk about the unified science architecture that we've got going on. With that, a unified orbital science station, it optimizes the scientific yield by combining the resources and expertise to capitalize on the expanded capabilities of a large station that can provide additional common consumables and crew time on top of the stable environment of orbital-based science, which we see even today in commercial opportunities. While customers contribute the experimental hardware, specialist crew training and transport, the collaboration streamlines operations, fosters flexibility, and maximizes research output. Sorry about that.
There's your cat.
And so you can see this unified science architecture is able to really capitalize on the benefits of the OCS system in order to fix all of the inherent problems before and to expand on the new capabilities going forward for additional science at a lower cost. As Sam said, it's cheaper to build, it's cheaper to design, it's cheaper to launch, it's cheaper to run across the board, where a customer can provide all of their side a lot easier, a lot cheaper, and the station can provide a lot more capability in order to complete whatever mission there needs to be, which has suddenly a lot broader and a lot deeper opportunity.
Now, we've talked a few times now about the ability to have a sort of plug-in unit of payload, whether that's racks, whether that's modules. And I just want to expand on that a bit further because that's something that is currently on the ISS. We have the Express rack where you can plug in a sort of PC-sized piece of equipment into what's called a mid-deck locker equivalent payload rack, which has power and cooling provided. We took that and said, that's great, that's really effective. It's been really, really useful for researchers on Earth to take a standardized payload interface and not have to deal with power conditioning and thermal conditioning, but it's small. And there's not very many of them. I think there's 24 on the ISS today. We can go a lot better than that. We can go a lot better than that with Orbital can. These numbers here are for the baseline configuration. You can go bigger. This is the smallest Orbital can. We've got 640 mid-deck lockers. The ISS has 24 of them. That's a lot. I believe Blue Origin's what's it called again, station? Cameron, you remember the name of this, don't you? The Blue Origin station, the Orbital Reef, has 400. And that's a multi-module, multi-launch, very complex station with lots of inflatable modules and so on. We're going straight in with a lot more than that. As well as providing that in a modular fashion, where you can have plug-in racks, like with the Express rack system, the racks themselves are plug and play. We've got 80 of them. The ISS doesn't have 80 racks total, including the ones needed for life support and so on. Racks are pretty good. You can fit a lot into a rack. This is a glove box that's using the ISS. You can fit a life support system into maybe 3 or 4 of them. But it's limited in size. It's about the size of a fridge. You can't fit some things into a fridge. You can't fit a centrifuge into a fridge. You can fit a centrifuge into an 8-meter diameter deck, that's for sure. We've actually got a design for a complete sleeping system that fits into a deck, where you can sleep in artificial gravity inside an orbital can station. It's doable. It's something that's completely possible with the architecture. Because of the modularity involved in the way that it's built up as a section of stacked barrels, you can insert massive equipment inside, like centrifuges or complete full-size mirrors if you want to make a telescope inside an orbital can station. Optical systems, very large things, maybe furnaces if you're doing material processing. Or if you want to go the whole way, just bolt on a whole module. There's 6 docking ports on an orbital can station. On the baseline configuration alone, we can fit a lot more. You'll see on the next slide. Slide after next, sorry. These are the equivalent of the multi-purpose logistic modules that were used in the ISS during the shuttle era, which was a brilliant innovation. It's an entire module on a space station, essentially, that is plugged into either the space shuttle's power and life support systems or the ISS. And it sits there for a few months doing research. You load it up on the ground with a complete set of research equipment, fly it to space, it sits there and fly it back again. It's genius. It hasn't been done since because the shuttle stopped flying and you can't fit one of these on a Dragon. You can fit 6 of them in one Starship. You can really start to play with it. Just think what you can do essentially with a shipping container worth of volume, which you can park at your company's headquarters, load it up with experimental systems, fill the whole thing with a greenhouse. You don't have to even fit in rack units in there. Drive it over to Starbase, plop it into a Starship, launch it. It's on orbit within the next week, connect it up, flies for 6 months, does the science, and flies back again. It's as simple as shipping containers around the globe on ships, but to space. And you can fit all the equipment in because of this modular architecture. The way that the commodities that the station contains are modular and provided on tap to the payloads. It really unlocks these research potentials that you can't get any other way with this kind of system. The benefits of this are obviously enormous. I skipped a slide. The benefits are enormous. It really lowers the barrier to entry by having this fully modular system at different scales. It means you can have small teams, agile projects that can build and fly in a matter of months rather than years. And the cost is a lot lower, which is obviously huge. As far as mission specialization, if you have larger volumes to play with, you can have longer duration experiments that are flying and then much more complex. I've done work with people working in space agriculture, and the current solution on the ISS that does space agriculture is about this big. That's the complete sum of human knowledge about zero gravity plant growth. Comes from something the size of a 3D printer. That's insane. We should have a complete greenhouse in space by now. And Orbital Can Station lets you do that effectively at no additional cost. There's no additional design requirements or additional design costs and design time to make that possible beyond what you need to do of essentially plugging the system you have into a module that already exists. And large scale is really possible here. You can go beyond the test bench. You can work with 2 or 3 crew maintaining your experiments at all times. Let's say you want to test making nanomaterials in space or nanoparticles. That requires a rig the size of a room that has a number of operators working full-time tuning process parameters. That's possible. That isn't possible today. There's no vehicle on Earth that can fly a payload that big with crew and maintain it on orbit for long enough to get useful data. Orbital Can Station can do that kind of science routinely, day in, day out, week in, week out, which is something that is really, it's a capability that isn't even planned in any of the next generation stations. Orbital Reef can't do it, the VAR stations can't do it, Chinese stations can't do it, because it relies on having the rapid mass to orbit, the high mass launch, a large station with all these modular functions on board that lets you plug and play with your commodities. It requires a complete system design change to get to this point where you can plug and play science this way. And I should say, like, we talked a lot about plug and play and about modularity. OCS isn't a design, it's a design system. This basic design we've presented here is a single Starship launch. It's roughly an ISS replacement in a single go. We were presenting it as, here's what you can do with one Starship launch, give us $10 billion and we'll build this for you next week. That's the starting point. You can start there and go a lot bigger. The obvious thing to do is just put more docking ports on it. That's possible. Remember, you can, and these modules here attaching on the outside here, you can fit 6 of them per Starship. You can get these up and down quickly. I mentioned before about how you can combine stacked barrels to make new designs. Here's an example of that. This is a 4 meter diameter module. Stretched it. That would require its own launch properly, or be bundled with a few others. That can be launched as a payload adapter, essentially as a docking adapter with lots of nodes on it, and as a storage volume. That can be launched. It takes almost no additional design cost to make that happen. Each of these is the size of the ISS Columbus lab, and we've just added 4 of them on in one go. That's plausibly one additional launch to make that happen. Show me another design that can do that. And of course, you can go bigger. Just bolt more cans on. The whole thing keeps going. Each of these universal berthing modules between these modules can fit a pass-through that fits up to 6 full orbital cans in one go. 600 kilowatts of power and cooling through those cables, through those coolant pipes. This is probably the limit you can go before you start branching it or having more solar panels on power towers or so on. But this is not that big. That's only 25 crew, 30 crew. That's what, 3 times the size of the ISS? Takes 4 Starship launches? With the cadence they're planning, that can go up in a year, maybe less. You can really start to build things up to these behemoth stations. And at this size as well, you start to get the benefits, because this is going to need Dragons flying weekly to resupply with equipment. Starships flying with cargo fit out every month. If you want to bring in a new multi-refrigerator sized experiment to do cryogenic sample testing in orbit, wait 2 months and it's flown. It's that easy. It's not the case with the ISS today, because we don't have the regularity of crew flights because it's too small. There's actually a sort of perverse logic where the bigger the station, the better it gets. And Orbital CAN has the capability to support enormous stations. There's nothing stopping you from going all the way up to orbital ring size if you want to, or artificial gravity ring, not orbital ring. If you want to make this thing a few hundred meters long, this one here is a few hundred meters long. You can spin that around its axis, spin it end to end, join them into a ring. Nothing stopping you doing that. The launch adapters for this are all designed to actually take launch loading. It's very possible to do it. You might need to do a bit of reinforcing on orbit, but it's not difficult. Orbital CAN provides the infrastructure and the payload and the basic design pattern that lets you build absurd stations to do absurd things, enormous orbital operations, whether that's manufacturing, shipbuilding, fit out before transit to Mars and the Moon, science at a scale that we can't even think about now. Wait till someone says, oh, I want to take an entire orbital CAN station the size of a Starship payload ferry and put one experiment in it. How much does that cost? Maybe 20, 30 million in the cost of the shell. The cost of the launch is maybe another 10 million, 20 million. That's the price of one Dragon seed today. You can launch an entire, something the size of a house to orbit as a fitted out space station module and have it work. That's what Orbital CAN system lets you do for science. It's something that no other design can do currently. And it's really revolutionary, not evolutionary, in its capabilities. Cameron, you want to take this one, or should I do this?
Yeah, I can absolutely. So, yeah, let's put it all together. And I will mention that the modularity is like the definition of the word modularity comes here. You can really expand this almost infinitely to the point that you have to start worrying about the orbital mechanics of such a large thing in orbit. You know, it is self-sufficient and modular. It just expands as you need it to exactly what Sam's saying, the point where you can want to fly something, design it. Your design life cycle is most likely going to take longer than it is for you to build it, for then it to just get up to the station and begin outputting that science that you're looking for. So yeah, let's put it all together and see that Orbital can, therefore, is a fully enabled, Starship-enabled space station. It is both cheap, it's efficient, it's easy to operate, and its inherent modularity allows you to effectively, ad infinitum, do whatever you want with that station, whether that's increasing crew, whether it's increasing science, increasing overall yield. You can really do anything. The sky orbit is not the limit anymore. This enables this large-scale, low-cost science in orbit that you can do as anything from those old ISS-style designs where you're within those kind of CubeSat form factors, or where you're in these glove box or fridge form factors, all the way up to full modules that are entirely dedicated Starship launches. And that is absolutely well within the realm and the future and now of the budgets of these large-scale primes or these large-scale researchers who all of a sudden don't need to do small on-orbit demonstrations to do pharmaceutical manufacturing. They can have an entire factory set up in orbit, low cost, cheap, and very, very fast. And then they're getting flights up there and flights back very quickly. So overall, this reduces the barriers for entry, not just to these large companies as well, who are going to be purchasing entire modules, but all the way down to the student and the institution and the open access, open source scientific community like Nexus Aurora, where we're able to actually feasibly say, we want to send an experiment into space and have it be running. We're going to do all the upfront cost and provide all of the experiment, and for a very, very low cost and a very low swap on the relative size of the OCS, we can access that, and it can be accessed by people across the entire world, regardless of where they are or what their means of access are, because it's just so low barrier to access all of a sudden. And so you can clearly see how that expanding science is going to have rippling effects across all industries, because space provides a uniquely stable environment and OCS provides a uniquely capable, modular, and scalable solution to expand that science and then bring that back to Earth for the good of humanity here, and for the good of expanding humanity again in further and further into space and expanding our capabilities there as well.
Thanks so much for having us. We'll take any questions, and I can't see any in the live stream, but if you've got any to ask us, we're happy to go through them.
Very insightful demo on Orbital CAN station. We do have some questions for you guys while you're here. First of all, we at DoraHacks, we're just so excited to see projects like this that are using Starship's heavy lift capacity. It will just fundamentally change the design process. Like during the design, the engineering design process, you probably won't need to focus on too much on the mass volume. Instead, you can focus more on the performance of your project. So we're really glad to see Orbital CAN station. I'm wondering, what are the next steps for Orbital CAN station? Also, I know that at Nexus Aurora, your projects can serve as like reference for further projects. What further projects are you guys looking forward to seeing that build on top of Orbital CAN station?
So if anyone listening has $10 billion, give us a call. We'll build one. It doesn't seem practical for us community of volunteers to build a space station, unfortunately. And we don't want to. The point of Orbital CAN was to look at design thinking and say, what can Starship do for us in the future? We don't think there's any advantage to getting down into nuts and bolts level design of it. We want to keep asking questions about what's possible in the long run, what should we be doing? And we feel that the Orbital CAN envelope really does a lot of work to help that. And we're really keen to start looking further at different systems within that, because asking, what can you do with life support systems if you have 10 tons to play with rather than 400 kilograms? That's interesting. That's an interesting question you can answer in simulation on a lab bench in concept design. Asking what exercise equipment you can build if you have more space to play with. There's more effective than current things that are very compact and tiny. We're very interested to look more in the future at the systems that go in these space stations, particularly the ones that are useful on Mars and the Moon as well, because Orbital CAN provides, we think, a building block. And we're really glad to see that in the past 2 years since we published these first papers, lots of companies now starting to rumble in that direction. We've seen Vast Space come out with a very similar looking welded design. We've seen Airbus come out with their, I forget the name of the module, but they've got another Starship launched barrel constructed station. We feel that the envelope is pushed on that, which is really good, and that's really something we're excited about. We want to start pushing the envelope on other systems now, whether that's habitation, life support, the actual science components within this, the actual lab benches upon which science happens, or interrelated things. We'll see whether that's crop growth, whether that's food. We've done a lot of work on cooking in the past. It's quite interesting. Things like that, basically.
Yeah. And to add on to that, we at Nexus Aurora specialize in doing this think tank incubation from large-scale hypothetical projects, and the output of those are often research papers or projects like this where we can provide architecture. And that serves our core mission because it allows us to put these ideas out there and hopefully see it be picked up, or at least inspire engineers and companies that do have the resources to look into this further and to bring it to space, because we're all about enabling that permanent space settlement. And if we can bring these ideas and say, this is something you should consider, that's absolutely, fits what we want to do. And with OCS, I think especially saw it. And, there's a clear opportunity with Starship for launching stuff into orbit, but to have our specific architecture be very closely mirrored by some of the companies we've spoken with since publishing this information was very good for us. And that allows us to be working on large scale projects that are more on paper, and then physical hardware systems, like those plants, like space toasters, all those individual systems that we want to put into a system like this that someone else can have the resources to build.
Got it. Awesome. Thanks so much, Sam and Cameron. I think, if in the audience, if you would like to work on some space projects, looking for teammates to work with, feel free to check out Nexus Aurora, join their Discord server. There are a lot of there are plenty of projects going on, and just engage yourself in the community. And also, if you're working on a community or organization who would love to work with Nexus Aurora, go talk with Sam and Cameron, reach out to them as well. I have one last question, two questions actually. You guys know that the round 2 of our Starship Use Cases Hackathon is ongoing until the end of July. What other use cases that are utilizing Starship's capacity are you guys working on at the moment, or will you be working on in the near future? And also for space in general, what sector is your guys most excited about in general?
I mean, for the first point, how many hours do you have? I think almost all of our projects are Starship enabled in one way or the other, because we focus very much on looking at the future of space exploration, and we see large, low-cost heavy lift as being the future of that. So we have a laundry list that is long for many of this. That includes a lot of stuff to do with space resource utilization, both on the Moon and Mars, mining, atmospheric processing, food production, chemical processing, metallurgy, machining, printing. That whole pipeline is very fascinating. We're on the fence about refining this design further versus making a new one for round 2, because we may well put in another handful. And cool. As far as what sector of space is interesting, personally, my background is in ISRU and resource utilization and thermal engineering. So I'm doing some interesting work at the moment to do with thermal control and resource extraction on Mars and some resource extraction on the Moon, which is very interesting. I think that's one of the fields where we're starting to see the wave of companies start to come through and pick up really interesting concepts to do, especially with lunar water mining and field processing, which I'm looking forward to in the next few years.
Got it. How about Cameron?
In reverse order, my background is in solid propulsion, specifically looking at active debris removal in orbit. So I very much come from the opposite end of everyone sending stuff into space, and a lot of my work revolves around getting that stuff back out of space, which is something we did touch upon in this presentation, was designing for deorbit and bringing things back to Earth. And that's where I'm largely interested at the moment, because things like Starship, things like OCS massively enable systems like that to be a lot easier to implement, and basically an orbital gas station from which you can deploy whatever you have to go and remove potential issues or potential orbital debris that is going to be around. And that's where I'm largely interested at the moment. As Sam said, for round 2, we're evaluating on drilling down into other potential applications and designs, as well as maybe more specific system level designs that can be used to leverage the advantage of something like OCS or Starship over the smaller, cheaper station, or smaller, more expensive stations that don't have that kind of capability.
Got it. We're looking forward to seeing more of your ideas from Nexus Aurora, and looking forward to see how we can further support your projects. And I guess I think I saw there is a question from the audience. Conrad? If you guys can briefly wrap up, I know we've touched on this during the session, but if you can share a bit more on what kind of science that can be enabled by a cheap, large station and not with ISS, that would be appreciated. There is an audience looking for more answers.
Sure.
Yeah.
I mean, two of the big ones, literally the big ones, are material processing and biosciences. Your typical material processing experiment is the size of a warehouse, because the full-size system is the size of a factory. So being able to fit a complete metallurgy system into microgravity is difficult, and it's much harder if you have to fit in something this big. One would almost say you can't really fit a practical aluminium smelter into something that big. You can fit it into a complete ISS module, you can fit it into a complete deck. The same is true with bioscience, whether that's animals, whether that's plants. We've had experiments with mice on the space station that fit into a box this big, and the mice don't last very long, basically. Or you can't comfortably keep the mice in orbit for very long in that kind of space, and you can't grow very many plants in that kind of space. You want to have a greenhouse that you can fit a few tons of plants into, or fit a complete small ecosystem into with insects and plants and animals. That's not possible in the ISS just because of volume constraints.
Yeah, and beyond what type of science you can do, it's also about all of the upstream effects. So, you might be able to do the same science, but if you have a lot larger area to work with, if your constraints are a lot less, it's all about being able to access that same science, but a lot faster and a lot more cheaply. But to also use a specific example, what really jumps out at me are generally agricultural or biopharmaceutical needs, where space constraints can often be the end of consideration of space for a mission.
Definitely. Thank you so much for elaborating on that. Really appreciate it. I think we're coming up close to time here. So thanks so much, Sam and Cameron, again, for presenting Orbital Can Station. We're looking forward to seeing more of your ideas from Nexus Aurora in round 2. And before we wrap up, I just want to quickly highlight again that the submission portal for our Starship Use Cases Hackathon Round 2 is already open. We have prepared a prize pool of $100,000 and designed over 20 use cases and open challenges for you to tackle. We also have our space resources and exploration mini grant program in place to support everyone contributing to the space sector for the long term. The submission portal is open all year round. So we welcome everyone who has a passion for space to join us and shape the future of space exploration. If you want to learn more about us and our initiatives, feel free to click the links below in the description to our grant and hackathon pages. With that being said, I want to say just a huge thank you again to Sam and Cameron for joining us today. Really appreciate your time, and thank you to all the audience for tuning in today. We do have more space-related live sessions prepared for you, so make sure to follow us on YouTube or Twitter at DoraHacks so that you won't miss out on any updates. And also, if you're interested in learning more about Nexus Aurora, feel free to check out the website and join their Discord server to talk with the members there. And yeah, that concludes this demo session featuring Orbital Can Station, one of the winning projects in our Starship Use Cases Hackathon Round 1. So thank you so much, everybody. We will see you soon. Have a great one. Take care.